Okay, so we will continue with the problem solving sessions, and today we will continue some problems of true false type and short answer, and also if long answer type of questions on the second law of thermodynamics. So, first we will start with the true false problem. The first question is that for a fixed amount of a perfect gas, U and H each depend only on temperature. So, is it true or not? So, we know that for ideal gas system, U is Cv dt, and Cv for an ideal gas is nothing but 3 by 2 R, which does not depend, R is an universal gas constant, therefore, it does not depend on temperature. So, Cv does not depend on temperature and U then only depends on temperature, and H is nothing but Cp dt, H is nothing but Cp dt, and we know that Cp is nothing but Cv plus R. So, therefore, Cp also will not, for ideal gas Cp also will not depend on temperature, and therefore, H will only depend on temperature. So, this first one is true. Cp is a constant, we already discussed that Cp is nothing but Cv plus R, and for ideal gas system actually Cp is nothing but 3 by 2 R plus R, which is 5 by 2 R. So, it is a constant, and because R is a constant, P dV equal to nR dt for every infinitesimal process. Okay. So, the question is that for a fixed amount of a perfect gas, now for a fixed amount of perfect gas n is a constant, R is a constant, and so whenever we do P dV, so let us say the equation is, we will just go here to write it, equation is P v equal to nR T. Now, if I take a differential amount, so it will be d P v equal to d of nR T, which means d P dV plus V dP is equal to nR dt, because n and R both are constant. So, this is the equation that we have to follow. So, therefore, only P dV equal to nR dt is true only when pressure is constant or dP equal to 0. So, therefore, this is going to be false. Now, fourth one, Cp minus Cv for a 1 mole of gas is R, which is true, we know, and d equal to Cv dt for a reversible process. Now, of course, we know that for an ideal gas system d equal to Cv dt, but for a real gas system it is not true. So, the second question, for a reversible process in a closed system, delta S must be 0. So, we know that delta S is dq reversible by T. So, for a reversible process, we know that the entropy of the system is equal and opposite of the entropy of the surroundings. So, therefore, entropy of the universe will be equal to 0. However, for the system it depends on the type of the system whether the delta S will be 0 or not. So, therefore, we cannot say for sure this particular question. For a reversible process in a closed system, delta universe must be equal to 0, and that just now we have discussed that is true. For a process in an isolated system, delta S cannot be negative. Now, any process in an isolated system, we know that if it is spontaneous process, or for example, any process that happens in an isolated system, there is no external influence. For example, you talk about our universe is an isolated system, and in that any process that happens has to happen spontaneously, because there is no influence from outside, and therefore, if that happens, we know that entropy has to be always positive. So, therefore, it cannot be negative is a right statement. For a closed system, next question, for a closed system, equilibrium has been reached when S has been maximized. Now, we know that for an isolated system, when the system reaches to equilibrium, the entropy becomes maximum. However, for a closed system it may not be true, because in a closed system it depends on both the energy and the entropy. We will understand that later, that something else rather than free energy will be negative or maximum negative in this particular situation where it becomes equilibrated. So, we will discuss about that later on, that however, for this it is not true. In every cyclic irreversible process, the final and initial states of the system are same and the final and initial states of the surrounding are same. Now, when I talk about a cyclic process, then the final and initial states of the system has to be the same, because the process happens. We are talking about the state function of the system, which will become the same when system will come back. However, something else happened to the universe. In every cyclic irreversible process, the final and initial states of the system are same. However, the surrounding is not the same. Q is 0 for every cyclic process, which is not true. We know that Q is not a path function. So, Q may not be 0, and again for Carnot cycle you know that Q is Q1 minus Q2 for that cyclic process of a Carnot cycle. Delta S for an irreversible change of 1 mole of nitrogen from 10 liter to 20 liter at 25 degree centigrade must be same as delta S when 1 mole of nitrogen gas goes reversibly from 10 liter to 20 liter at the same temperature. So, the question is that whether or not an irreversible process going from A to B and a reversible process going from A to B will have same entropy or not. So, remember we discussed that even if the process is irreversible, we have to construct the corresponding reversible path and calculate the entropy. So, therefore, even for the irreversible path, the entropy is calculated from the reversible path. So, they have to be the same, because the calculation itself will depend on the reversible path. So, this is a true statement. And also you should know that you know that the entropy is a state function. So, therefore, it does not matter whether the process is reversible and irreversible, as long as the initial and final states are the same. Next question, thermodynamics cannot calculate delta S for an irreversible process. Again we know that in order to calculate such entropy, we have to construct a reversible path, and therefore, we will be able to calculate that as long as we have well defined initial and final states. This is wrong. Increasing the temperature of the hot reservoir of a Carnot cycle engine must increase the efficiency of the engine. So, we know the efficiency of the engine formula, right. Efficiency of the engine is 1 minus T2 by T1. So, where T2 is the temperature of the cold reservoir, T1 is the temperature of the hot reservoir. What is the question? Increasing the temperature of the hot reservoir, which means we increase the T1. What will happen if we increase the T1? T2 by T1 will become smaller, efficiency will increase. So, increasing the temperature of the hot reservoir of the Carnot cycle must increase the efficiency of the engine, which is right. Decreasing the temperature of the cold reservoir, again if we decrease the T2, what will happen? T2 by T1 will become smaller, eta will increase, must increase the efficiency of the engine, which is also true. The work done in a Carnot cycle is 0, which is not true, because you remember the work done in a Carnot cycle is actually area enclosed by the curve, which is also the heat change in the Carnot cycle process, which will only be 0 if there is no area left, and that is only possible if there is no adiabatic process happens, right, because you need the whole path, and only when the temperatures are same, or rather the first isothermal step is traced back, then only work done will be 0, otherwise it is not a right answer. So, now we finish the true false type of questions. So, you see the similar type of questions will come, and you have to use the logic, the same logic that we have used in order to answer this particular questions. Remember the logic behind each question and think physically to understand what is going on, and that is what we were trying to explain during explanation of each and every answer for these questions. Now, we are going to come to some simple short questions, just to these type of questions can be understood if we know the formula and if you can catch the right place. For example, let us see this one. Which state function must remain constant in Joule's experiment? Okay, this is a knowledge based question. So, you have to know that internal energy U remains constant. Which state function must remain constant in Joule-Thomson? You know that it is the enthalpy. So, this is something that you have to know. Second one, a container is filled with an ideal gas at pressure 1.5 atmosphere. The gas is compressed isothermally to 1/4 of its original volume. What will be the new pressure of the gas? So, initial pressure, okay. So, now you see we are talking about an ideal gas. So, you have to use an ideal gas equation P v equal to nRT or P 1 V 1 equal to P 2 V 2, and we know that initial pressure is 1.5 atmosphere and the gas is compressed isothermally to 1/4. 1/4 means we know that V2 by V1 is 1/4, which means P2 by 4. So, what will be the pressure? Pressure will be 1.5 into 4 is 6 atmosphere. Okay. Third question, the state of an ideal gas was changed 3 times at 3 different temperatures. Let me just erase this one, so that we can see that. So, this is the figure that is given here. The state of an ideal gas was changed 3 times at 3 different temperature. The diagram represent 3 different isothermal curves. What can you tell about the temperature of the graph? Now, you see PV equal to constant is the equation of ideal gas. However, there is something, therefore, if you draw P against V, you will get something like is called rectangular hyperbolic equations, which go like this. Each equation will go like this. However, you have a temperature associated with this one, which means that if you increase the temperature, your PV value will increase. So, which means that let us say for when you increase your temperature for any given volume, because let us say we can write P as nR T by V. So, when you increase your temperature for any given volume, if the volume is fixed, your pressure will increase. Now, let us talk about this particular volume. Then in this case the pressure is smaller, but in this case the pressure is higher. In this case the pressure is even higher, which means this must be T3 must be greater than T2 and T2 must be greater than T1. Okay. Find the molar volume of an ideal gas at 20 degree centigrade and 1 bar pressure. Now, molar volume of an ideal gas at 20 degree centigrade and 1 bar pressure. So, how do we know that? So, again we are going to the equation, ideal gas equation, P V equal to nRT. Now, we need to find out molar volume. So, which means we need to find out V by N, V bar equal to RT. We have the value of R, we have the value of temperature 20 degree centigrade, and we have the value of pressure. So, we have to get the volume, molar volume RT by V. Now, we have to simply put the value, which is 8.314 multiplied by temperature is 20 degree. Now, there is a catch here, because it is not centigrade, we have to use Kelvin unit, which means 20 degree means 293 Kelvin divided by 1 atmospheric pressure. Now, 1 atmospheric pressure, now what is the unit here? So, for example, here unit is joule per Kelvin. So, I need to go there. So, V bar equal to RT by P, sorry P. So, now pressure is 1 bar pressure. So, 1 bar pressure is, so we have to convert everything in joule and Kelvin. So, we have to convert the 1 bar into some joule per liter pressure. So, this is 100 joule per liter, giving rise to 8.314 multiplied by 293 by 100 liter, that will be the volume, and let us calculate that how much that comes. Let me use a calculator, is 24.36 liter. So, that will be the answer. Okay, next question, calculate the temperature change of 1 mole of an ideal diatomic gas contained in a piston where Q is 65 joule and W is 210 joule. Now, we know in first law of thermodynamics U equal to Q plus W is actually change in internal energy U, and we know Q is 65 joule and W is 210 joule, which is 275 joule. Now, we will use the formula of U as CV delta T. delta T is the change in the temperature and Cv is the specific heat of a diatomic ideal gas. So, therefore, delta T will be equal to delta U by Cv, which is 275 joule by Cv. Now, Cv for a diatomic gas is 5 by 2 R. So, which is 275 joule divided by 5 by 2 into 8.314 joule per Kelvin, which will be equal to, let us do the calculation. So, 275 divided by 5 by 2 is 2.5314, which is giving us 13.23 Kelvin. So, 13.23 Kelvin is the answer. That much temperature change will happen. Okay, next question. If an electric motor produces 15 kilojoule of energy each second as mechanical work and lost 2 kilojoule as heat to the surrounding, then calculate the change in the internal energy of the motor each second. So, we will go here. So, it is 15 kilojoule. So, we know that delta U equal to Q plus W, right. So, where W is 2 kilojoule minus 2 kilojoule and it is the work done by the system. So, that is minus 15 kilojoule each second. So, it is minus 17 kilojoule each second. So, that is the answer to the question. Next one, a mole of water vapor initially at 200 degree centigrade and 1 bar undergoes a cyclic process in which work done is 338 joule. Find Q in the process. So, here again we have to use the first law of thermodynamics. So, water vapor that is initially at this temperature. So, it goes a cyclic process. So, if it goes through a cyclic process, we know the internal energy remains constant, and if that is the case, then the Q will be nothing but minus W. So, therefore, we do not have to do any calculation, we can say that the Q will be minus 338 joule. Determine the heat to be supplied to a Carnot engine operating between 400 degree centigrade and 15 degree centigrade and producing 200 kilojoule of work. So, we know that in Carnot engine the heat input by heat output is proportional to the ratio of two temperatures of the two reservoirs, right. So, T 1 by T 2, where Q 1 is the heat input to the engine, Q 2 is the heat output from the engine, T 1 is the temperature of the hot reservoir, T 2 is the temperature of the cold reservoir. Now, as you can see here, we have been given the temperatures here, which is 400 degree centigrade means 400 plus 273 is 673 and 15 degree plus 400 is it will be 288 Kelvin, and now producing 200 kilojoule of work. So, and we have been also given the work which is Q 1 minus Q 2 to be 200 kilojoule. Now, we have two information. One is that Q 1 minus Q 2 is 200 kilojoule, we need little bit more space. So, I will go there. So, Q 1 by Q 2 is 673 by 288 and Q 1 minus Q 2 is 200. So, these are the two informations given, and this is like two unknown two equations scenario. So, we can always write Q 1 equal to 200 plus Q 2, we can put that in equation 1. So, 200 plus Q 2 by Q 2 is 673 by 288. So, 200 by Q 2 plus 1 is 673 by 288. So, 200 by Q 2 is 673 by 288 minus 1 is how much. So, 385 by 288. So, Q 2 by 200, 288 by 385 So, giving rise to Q 2 equal to 288 into 200 by 385. We will just do that using calculator. 288 into 200 divided by 385. So, we are getting 149.61, and naturally we are going to get Q 1 equal to 349.61, that is kilojoule, and this is also kilojoule. So, we got that. So, heat to be supplied will be 349. Okay. So, that we got. Now, continuing with this short questions, a body at 200 degree centigrade undergoes a reversible isothermal process. The heat energy removed in the process is 7875 joule. Determine the change in the entropy of the body. So, now what kind of problem it is basically that it is an isothermal process. Okay. So, and the heat energy removed in the process is also given. So, heat is given, temperature is given, we have to calculate the entropy. Now, we know the formula of entropy is delta S equal to dq reversible by T, and we have been given the dq which is 7875, provided of course, this dq is reversible. It is mentioned here that undergoes a reversible isothermal process. So, we are just taking it to be reversible. Okay. We do not have to do anything here. So, this is joule per Kelvin, because that is a standard unit we have to use. So, 200 will be converted to Kelvin, which is 273 plus 200 is 473 Kelvin, and the value will come out to be 7875 divided by 473 is 16.65 approximately 16.65 joule per Kelvin. See, this is the unit of entropy, however, okay, joule per Kelvin, that you have to remember. Next one, helium stored in a container under pressure 10 megapascal starts to leak. I will just remove this answer. Starts to leak slowly through a broken valve until its pressure drops to the atmospheric pressure of this much. The whole process proceeds isothermally at room temperature 20 degree centigrade. Find the change in the entropy for this ideal gas of weight 1.0 kg. Now, what are the approaches one can take in this particular process? First thing to note down is that the process is isothermal process. So, if you remember, and of course, although we have taken helium gas, but we said that for this ideal gas, meaning take the helium gas to be an ideal gas. So, we have to know the formula for calculating the entropy for an ideal gas system. Now, if you remember, the formula for calculating entropy for an ideal gas system is nR ln V2 by V1, where V2 is the final volume, V1 is the initial volume, N is the number of moles, R gas constant, and things like that. Now, also we know that, so but here we have not the question does not give you the initial and final volume, but initial and final pressure. So, you also know that P1 V1 equal to P2 V2 for an ideal gas. So, therefore, V2 by V1 is nothing but P1 by P2, so which means initial pressure by final pressure. So, we can write nR ln P1 by P2. P1 and P2 are given, R is known, but we have to still calculate the N. N is number of moles. For that, what is given is this particular thing 1 kg. So, we know that molecular weight of helium is 4, So, therefore, number of moles here is 1 kg, which is 1000 gram divided by 4, which is will be 250. Okay. So, now we have to put the initial pressure and final pressure. We do not have to care about the unit, only thing we have to make sure that they are on the same unit. So, we know the number of moles will be 250, R is 8.314 into ln of 10 megapascal is 10 to the power 7 Pascal by 101325. Now, let us calculate how much that comes. So, 250 into 8.314 into ln of 98.6923, giving us 9544.48 or 49 joule per Kelvin. That is what we get. So, we will go to the next question. Next question, a refrigerator operates on reverse Carnot cycle. Determine the power required to drive refrigerator between temperatures 42 degree centigrade and 4 degree centigrade if heat at the rate of 2 kilojoule per second is extracted from the low temperature region. Now, in order to understand this particular question, let us draw this. So, a refrigerator operates on a reverse Carnot cycle. So, Carnot cycle has to be reversed, which means that now it will take the heat from low temperature reservoir and throw the heat to the high temperature reservoir. Let us call it T 1 and T 2, and we know that we need work done, otherwise it is not possible. So, power is nothing but work done per time, work by time is the power. So, power required. So, first we have to calculate then the work done, right. So, power required to drive this thing between the temperatures 42 degree and 4 degree centigrade if heat at the rate of 2 kilojoule per second is extracted. So, we know that Q 2 equal to 2 kilojoule per second. We have to know what is the Q 1 and the temperatures have been given. So, we know from Carnot cycle is Q 1 by Q 2 is T 1 by T 2. Now, what is Q 1 we do not know, Q 2 we know as to be 2. So, I will put that value as 2. T 1 is the high temperature, which is 273 plus 42 degree, and this one is 273 plus 4 degree, giving us 315 by 277. So, Q 1 is 315 by 277 into 2. So, which is 630 by 277, which is if I do the calculator I will see that 630 divided by 277 is 2.274 kilojoule per second, that is a Q 1. So, therefore, W equal to Q 1 minus Q 2, which is 2.274 minus 2 kilojoule per second, or W by power, rather power equal to W per time, which is 0.274 kilojoule per second. Okay. So, we have done that. Next question is, oxygen is compressed reversibly and isothermally at 27 degree centigrade from 125 kilopascal pressure to a final pressure of 375 kilopascal. Determine the change in the entropy of the gas. We have already discussed a similar problem, that if that happens isothermal process, then entropy change is N R ln P 1 by P 2, initial pressure by the final pressure. Now, N is it given N? So, here it is saying that N is not given. So, we will just assume to be 1 mole, and then it only boils down to 8.314 multiplied by ln of final pressure is 375, initial pressure is 125. So, 125 by 375. Okay. So, then you can do the calculation and then solve that, because it is straightforward. Next question, determine the change in entropy of the universe if a copper block of 1 kg at 27 degree centigrade is dropped from a height of 200 meter in the sea water at 27 degree centigrade, means the same temperature, and heat capacity is given. Now, you see when you drop a copper block from certain height, the potential energy of the block will hit the ground, it will convert to the kinetic energy, and then when it hit the ground it will convert to the heat, right. So, we have to know basically what is the potential energy of the system, and then we will be able to, we will assume that all are converted to the heat, and then we will be able to calculate the change in the entropy of the process. So, one thing just I would like to tell you is that this process is not a reversible process. However, we are calculating the entropy change of the universe. So, here is a catch. I will come to that about this particular question. First, let us calculate the heat that is going to the universe. So, here the dq is nothing but du, which is mass mgh, m into g into height. So, mass of the block is 1 kg, g is 9.8 meter per second square, and h is 200 meter. So, that will give rise to a value in joule, which is 196 then 200. So, 1960 joule, that is the dq we get, like q we can say q we get, and then the temperature is 27 degree centigrade. Now, it is an irreversible process, okay, because the q, so the fallen block will never come back. So, it is an irreversible process, but universe is very big. So, even a process that is happening irreversibly within the system and there is a change in the q, it is taken to be a reversible process for the universe. For example, I talk about a system here, and let us say there is an irreversible process going on from A to B, let us say, and let us say there is a change in dq, irreversible dq. So, therefore, we will not be able to calculate from this process alone the entropy change for the system. However, let us say this change in the q and it throws away q amount of heat to the universe irreversibly for the system. However, we take that to be a reversible change for the universe and we will be able to calculate the entropy change. So, delta S here will be nothing but the q by T. Now, q is 1960, T is 27 degree, which is 300 Kelvin, that is the joule per Kelvin entropy change. So, okay. Okay. So, that is an important point that we have to remember, and because of that only we can see that an irreversible process, the entropy of the universe will be positive, otherwise it will not be positive. So, the fact that a small irreversible change or for a system a large change is extremely small for the universe, because you see whenever there is a change in the heat, we have to see how much change that happens for a particular for our universe. For example, if I take out a glass of water from the ocean, it is a very extremely small change for the ocean. However, for a system with a bottle of water, it is a huge change. So, that analogy is used. So, whenever we talk about an infinitesimal change, it is with respect to the system alone. If the system is big, then the changes can be infinitesimal even if it is finite for a smaller system. That is what we have to understand.